Right, thanks for joining me. In this video, this is part 2. Hang on, the Duchess has arrived. Welcome back. This is part 2 of this little video series about my trials and tribulations with an electric power drawbar. So let me explain further what I've been trying to do and how this particular drawbar works, and we'll get into it. So roll the titles and then I'll explain. Let me explain a little bit about the drawbar in my little Sile CNC mill. That's not a good start. Let me explain a little bit about the drawbar in my little Sile mill. This is it. Not particularly complicated, just a piece of reasonably tough steel that's getting a bit manky. Right, that goes through the top of the spindle. Let me do that again. That goes through the top of the spindle, and on the bottom it screws into this, or one of these. This is, in this case, it's a 90mm R8 collet. And what you do is so you've got this this assembly, and you put your tool in the bottom like so, and you do the nut up on the top. That draws the collet into its socket, and in doing so it grips. Just even with a bit of hand pressure you can get some quite significant gripping force. These collets, this is going to be really difficult to pick up, but they actually the taper forces them to shrink slightly because they're cut through in these ones in 3 places. So your tool, in this case one of my tool holders, slides in, you do the nut up, and you apply a force between this flange and the taper, and you lock the tool in position. That's fine and dandy, and that works brilliantly. In fact, nearly all milling machines, all of the DIY machines I think do this, and you know, it's a standard in Bridgeports, all that sort of machinery. However, in the CNC world, it's a pain in the butt. It really is, because every time you want to do a tool change, you have to put a new tool in, then you have to go through the process of measuring its length. So it gets tedious. It's less tedious with tool holders like these, because these register on the bottom flange of the spindle. So if you know the length from that flange to the end of the tool, you can just recall that tool out of your tool library, and that speeds things up. However, every time you want to do a tool change, you have to go to the mill, wind it clear of the work, undo the drawbar, give it a little tap on the top to release it, the tool falls out, put a new one in, do it all up, recall the tool, offset, and away you go. Now that takes, if you're reasonably quick at it, you can do it in a minute or so, 50 seconds, minute. But I find it bloody tedious. So this is where I've been going with it. I've been working on this for well over a year, and this is my replacement drawbar. So this drawbar comes out and is replaced. That's history, get rid of that. Replaced with this drawbar. Now, the only difference is this has a sliding collar and what look like a load of thick washers. Well, these are actually called Belleville springs, and they are I think some people call them disc springs, but they you stack them in various combinations to give you various forces, and this seems to be the best combination for me. So I've got 8 of them, 2, 4, 6, 10 of them, sorry, and they're stacked so that one's facing up, one facing down, and that gives me the maximum movement, which is what I wanted in this. Now, it works in exactly the same way as a standard drawbar, except you tighten it up and you apply the same clamping force that you would normally apply to hold the tool in. However, with this particular arrangement, if you can apply force, now the simple method to do this is just to push the end of the drawbar. However, in doing that, the bearings sit here and here on the spindle. You put an awful lot of pressure on those bearings, and it can be significant forces. This drawbar is capable of putting 1.5 metric tons of force, if my calculations are right, and they're probably not. So that's a significant axial force to put on a bearing, particularly if you want it to remain a precision bearing. So this collar is designed, it's got a what do you call it, a flange on it. So if you can apply your force between there and there to squash these Belleville springs down, the tool will pop out the end. So that's the theory, and that led me to my first attempt. So let's just slide that out of the way a bit. This is my first attempt. I scoured the internet looking for the most powerful and shortest throw linear actuator I could find, and this one is rated at 500 newtons. That means it can shift or hold 50 kilos. So all this thing does is it contracts or expands to a set point, and I've got a power supply that you can't see and a switch, so turn it on. Right, here we go. There you go. That is all the linear actuator does. It just goes from one end to the other and stops. So the drawbar sits, actually I can do better than that. I can put it together. Let's do this. Put a nut on the end. There we go. Right. I don't know how particularly visible that is, but that's the basic arrangement. And on the top here there was an extension piece, and I ran this in the mill for quite a while. So we've got 50 kilos of force pushing this way, and we've got a mechanical advantage lever here of just over 10 to 1. So now we're up to 500 kilos pushing down on the drawbar. 500 kilos I thought was going to be enough, and to be perfectly honest, it worked a treat. However, if you up here somewhere, I'll put a link to the problem I had with it. It may have even been this tool walked out of the collar, so it slowly came loose. It slowly, over a period of time, just moved out of the bottom of the collet because there wasn't sufficient clamping force. So I thought, yeah, I really need to redesign this. Also, this was not beefy enough. It's bent that shaft that applied the force on the drawbar. So let me just put that to one side, and this was my next attempt. This was a similar sort of arrangement. Again, whoops, let me just put it together so you can see it. Whoops. Well, hey, Drawbar goes through there. Belleville springs sit on the top. You can see what happens. This is a threaded jack screw that fits in underneath there, and if you rotate this, you push the drawbar down. Now that, I thought, was going to do the job. I ground up some tools and made a square thread with a 2mm pitch, and the only thing I can say is I had to apply so much force that I bent. There you go. I bent this plate. I've turned it the other way around and tried to straighten it, but that's 6mm steel. So you can see the kind of forces required, and I thought I could squash this down and make it work, but the force required to do the push this screw to release the tool was phenomenal. So I thought, this isn't going to last long, it's not going to work very well, and to be perfectly honest, I was no better off than actually just using a standard drawbar and just loosening and tightening it as required. So that was junk. Put that out of the way. That was a few hours of well spent time, I can tell you. So I thought, I read some bits and pieces on the internet, and I thought, I need to multiply the force. So this is just a cobbled together thing to multiply the force. What it is I think that's 8mm. That's an 8 or 10mm hole that's been bored and reamed. This is a shaft that slides in there. I put a couple of O-rings on to seal it, and at this end we have a piston with a couple of O-rings, and the surface area of this is 1/10 of the surface area of that. So what I've done effectively is multiplied the force. This moves 1/10 of the distance but 10 times the force. So if you put 50 kilos into there, you get 500 kilos of force out of this end. Brilliant. That means that I can reduce the power needed to drive the piston in. I thought I can make a better job of this by properly engineering it and making it so that it fits my machine. So put that to one side. So I made this. Now that's a 12mm hole with an O-ring in the middle, and I think that's about a 48mm, 43mm, something like that, piston with, again, a brace of O-rings on it, and it's full of oil. Heads. Right, this, I needed a piston, so I made a piston, 12mm. Americans would call this drill rod. In the UK we call it silver steel. I cut a hex on the end, and the piston, the 12mm silver steel, is just locked in with a simple grub screw. So that fits in there and screws down. This moves 5 centimeters, 50mm. This moves 5mm because it's I kept the 10:1 ratio. So if you can apply 500 newtons, 50 kilos to this, you get 500 kilos or 5,000 newtons out of this end, but it moves 1/10 the distance. To release the tool, you only need to move literally a couple of millimeters, if that. This worked an absolute treat, but has been difficult to set up because the piston's recessed and it's all too long. By the time you've got this attached to, oh, I made a new base, there we go, there's the base, so that fits on there like that. The drawbar goes up through the middle like so. Yeah, so the Belleville springs sit in there, you screw it down and it works. To screw it down I used a 21mm socket and my trusty old Makita. Now that works brilliantly. There's enough torque out of the drill to make this work. However, I still needed a bit more force. I needed the drawbar to be a bit tighter. So I went and bought myself, I went and bought myself a drill. And here's the bones of my drill. This is the cheapest impact driver I could find. It's branded McAllister. This in the UK comes from I think it came from a distributor called Screwfix. Screwfix is owned by the Kingfisher Group, and if you look up the Kingfisher Group in your own country, this will be available, but it'll be branded differently almost certainly. But Kingfisher have outlets in America, Australia, Europe. They're a big operation. So this is their budget impact driver, and what I'm going to do is this is capable of 100 Newton meter, I think, 100 Newton meter torque. So if you apply 100 Newton meter to this hydraulic multiplier, you should be able to get 1000 Newton meter out of the bottom. So 1000 Newton meter is basically a metric ton. Is that right? 1000. Anyway, may have gone wrong with the maths there. I'll see if I can put a graphic up to show you how the maths worked out. This was, I think, about £60, which is just shy of what, about $55 or so, and it came with 2 batteries and a little charger. Well, this is quite useful because I'm going to redeploy these batteries in another project, something coming up in the future. So it's worth doing just for the batteries. I've got a low, they're 27 watt hour lithium ion, 18 volts. That's quite a useful size for me for another project. Anyway, put that to one side. 18 volts drive into this motor. Now I'm going to overdrive it. I'm going to drive it with 24 volts, which is a 30% overload. The duty cycle, if you're using this as a drill, you'd quite happily sit there for half an hour until the battery was flat, whapping screws into things, and you wouldn't worry about it, and it would get warm. On my CNC mill, I think that the duty cycle will be so low that it won't even get that warm. So I'm not overly fussed about overdriving it by 30%. So I have designed in CAD, I've been working on this for what seems like a bloody lifetime, a squashed version of this that will hopefully fit on top of my mill, because I'm limited with the head height as well. I can't go too tall because if I do I will hit the ceiling. To that end I have engineered, whoops, sorry about that. I've engineered a base plate That's the base plate. This piece is trash. That fits on there, and will move up very slightly. These springs, these screw springs, hold it in place. It will move up very slightly, and then it will clamp the spindle, and the hydraulic cylinder, that will be the new hydraulic cylinder, will sit on the top here, will push the drawbar down. Hopefully I should get, I'm aiming for about 1,000 kilos or more if I can manage it, which is a significant force, and that should hold any tool that I'm likely to fit in the mill in place. This has a little bit of an extra piece on the bottom, and here we go. On the mill, there's I made a flange that has a magnet in it, and this is Matsushita, which sounds rude, but is actually Panasonic. That's a Panasonic magnetic sensor. So that screws in through the bottom and is flush. So once this is assembled, we can pick up the rotation of the spindle. That means that I can feed the output of this directly into Mach 3, so I could get speed feedback, which I've done anyway. Also, it would be possibly an advantage, and I need to experiment with this, but it might be an advantage to use the step function on the variable frequency drive for the spindle, to keep just hitting it until you get the magnet sensor to say yes, the magnet is now over top of the sensor. So in other words, you get a positive signal. If you do that, then you will always put the tool in the same place. That's for the future, but it might work. I'm not really sure whether or not I can achieve it. Anyway, more to the point, I am now in a position where I can start manufacturing the parts for the new drawbar. So yeah, we'll see you over at the lathe, and we'll start cutting bits and pieces up. Contrary to what I just said, I think I'm going to end this video here because it's about 23 minutes long, and that's too much, I think. So 23 minutes of me is enough for anybody, including my wife. So hopefully that explains a little bit more about what I'm trying to do here, and some of the troubles that I've had thus far. In the next part, we will start the build of this, which is my current iteration of power drawbar. A spoiler is it doesn't work properly yet. However, I still have a couple of pieces to manufacture to finish it, so I will do that and add that to the next video. In fact, I'm not completely convinced that this is going to work well enough anyway, so I may well junk the whole idea and come up. I've got another idea which might well solve the problem. But ultimately, I think that it's distinctly possible to make a cheap power drawbar that's electric for these small hobby mills. I think it's definitely doable, and you know, at the end of the day, it's a couple of years worth of development time, and it's a bit of an intellectual problem as well, if that's the right terminology. Anyway, thanks for watching, and please hit the bell and subscribe button, and we'll see you again on the next one. I do appreciate you watching, so thanks very much, and ta-ta.